Welcome to presentation 15. Today we're going to be talking about the Serial Peripheral Interface SPI. As usual, I'd like to start by showing the architecture. The SPI is part of the layer 2, and the items in green are the ones that I've always presented, and this item in yellow, which is the SPI, is what I'm going to be presenting today. So what is going to be the agenda? First, I'm going to give you a little bit of background on the SPI. Next, I'm going to talk about the SPI related registers and how to configure them. And next, I will develop the framework. And finally, we'll go through a sample program. So let's go through the background. So SPI is a communications protocol used to send data between devices. It is often used for short distance communication in embedded systems. SPI works in a master-slave configuration where one device, which would be the master, controls the communication, and one or more devices, which would be the slaves, respond to the master command. For example, if you have a microcontroller, which is the master, connected to an SPI-enabled temperature sensor, which would be the slave, then the microcontroller can transmit a command to the sensor to request temperature reading. The sensor would transmit the temperature data back to the microcontroller over the SPI. So let's look at all the registers and see how they work. So I'll start by enumerating them. So we have the SPI control register, SPI status register, and finally the SPI data register. So let's talk about the SPI control register. With the SPI control register, you can enable the SPI, and that would be by setting the SPE 0 bit to 1. Next, you can set the device to be a master or a slave, and you do that by putting an MSTR0, putting a 1 into that bit for the device to be a master, or a 0 for the device to be a slave. Next, you have the SPI rate select. The SPI clock SEK is generated by the master device, and all data transfer are synchronized to this clock. The slave does not have control over the clock speed. The master has to set the clock rate that the slave can handle. If the clock rate is too fast for the slave, it may not be able to keep up with the communication, leading to errors. The clock speed is set by dividing the system clock, which in this case is 16 MHz, using clock divider option. These options are controlled by 3 registers. The SPR0, I should say 3 bits. SPR0, SPR1, which are located in the SPCR register, and bit SPI2X, which is located on the SPSR register. So what I'm saying is that the clock rate is controlled by the master, and the speed has to be in such a way that the slave can handle. If it's too fast, the slave is going to start dropping messages. So you go as fast as you can, but it has to be something that the slave can handle. So now let's talk about setting up the speed. So we have this table that shows you how you set up the speed. So for example, if you want a clock to go at 4 MHz, then what you would do is you would set the SPR 1 to 0, SPR 0 to 0, and the SPI 2X to 0. And that would give you 4 megahertz, which is your system clock divided by 4. So let's see the example. Setting the SPI clock rate to 4 megahertz. So that means the system clock divided by 4. So how do you do that? So first you go and set the SPR1 and SPR0 to 0 in the SPCR register. Then finally what you do is you set the SPI2X to 0 in the SPSR register. So let's continue. We have to set up the clock polarity, which determines the default state of the clock line when no data is being transferred. So if no data is transferred and you want your line to be always low, then you set your CPOL to 0. Now if you want the line to be high when it's idle, then you set the CPOL to 1. Now the most important thing about this parameter is that the master and the slave have to match. Now we have another parameter, which is the clock phase, determined when the data is sampled, which is read, and when it's going to be shifted, which is written, relative to the clock edge. So we have two possibilities. We set the CPHA to 0, which is data is read on the leading edge of the clock pulse and written on the trailing edge. Or you can set up to 1. Data is written on the leading edge of the clock pulse and read on the trailing edge. So they are the positive. Now the important thing about this parameter again is that the slave and the master have to match. Now to make it easy to set up your microcontroller, what they've done is they've given the combination of CPOL and CPHS modes. So what I mean? So if your slave set has to transmit in mode 0, then you know that your CPOL has to be equal to 0 and your CPHA has to also be equal to 0. If your slave says mode 1, then you have to use these values. And you have mode 2, you have to use this value, and then you have your mode 3. So these are the four modes. So when you see your slave said, hey, you need to set up to mode 2, then you know what are the values for your polarity and your phase. Let's go through an example. So if we have the slave says, hey, you need to be in mode 0, then you know you have to set your CPOL equal to 0 and your CPHA equal to 0, which means that you have to set up the CPOL and the CPHA to 0 in your SPCR register. Both master and slave devices must set to the same mode to ensure proper communication. And finally, always check the sensor data sheet to find out the correct CPOL and CPHA setting or the SPI mode number. Many sensors use the SPI mode 0 because it is straightforward, with data being read on the rising edge of the clock pulse when the clock is low at idle. So the nice thing about mode 0 is that your SPI by default is going to be mode 0 because the CPOL is going to be 0 and CPHA 0. That's at startup. So now let's go to the status register. This register shows the current status of the SPI. It is useful for checking whether data has been successfully sent or received. Usually what you do is you transmit data and then you go into a while loop waiting for the flag to get set or you use an interrupt. But looking at the flag when the communication has completed, then you know you can send something else. So the name of the interrupt flag is the SPIF, indicates when data has been sent or received. We have another flag which is the WCOL, shows if there was an error because the microcontroller tried to send new data before previously one was done. So let's talk about the SPI data register. Data transfer between the master, which is the microcontroller, and the slave, which would be another sensor or a microcontroller, happens simultaneously. When the master sends a byte of data to the slave sends byte back to the master at the same time. This is called full duplex communication. If the master wants to receive data from the slave, it must send data out at the same time. If the master does not have any meaningful data to send, it typically transmits a dummy byte, often a FF hex or 00, just to generate the necessary clock pulses to allow the slave to send data back. Now what this is saying is, if you want to receive, you're going to receive data from the slave, but you don't have anything to send, then still you have to send something to generate the clock, because the slave doesn't have any way to generate the clock. The clock is generated by the master, and if there isn't a clock, there isn't communication. So let's look at an example. So let's suppose the SPI receive a single byte. So you are looking for temperature, so automatically the slave is going to be send you a temperature. So what do you need to do for this to happen? So first you have to send the dummy byte to initialize the clock, to start the clock pulse. So in the SPDR, which is the data register, you would put the FF hex. Next, you would wait for the transmission to be completed. That would be by checking the SPIF bit, which is the communications complete flag. Then once that's completed, then you place the data register into your data parameter. So once this is completed, you know that the transmission from the slave is also completed. And then you can take the information that is on the data register and put it into your variable. So let's look at another example. So we have a routine here, which the input is a buffer, or an array, and we send the length of the buffer or the length of the array. And then what we do is we do a loop from 0 to the length of the array, and for each, what we want to do is we want to fill up our buffer with the slave information. So what we do is we say, okay, for buffer 0 is going to be equal to transmit. So we transmit the dummy FF, and when that transmission is complete, the data is going to be loaded into the buffer. So let's look at the SPI transmit. So SPI transmit, what it does is returns the data register, the contents of the data register. So we have here the input is the data, which would be this one, this line. So the first thing we do is, as before, we place the data, dummy data into register. Then we go around and around on the while loop until the communication is completed. And once it's completed, we know that the data from the slave is now contained in the SPDR register, which is the data register. So let's look at the the key components of the SPI communication. So what we have here is 3 lines, which are the chip select lines that are connected to each of the sensors. So we have the master, which would be the microcontroller. We have 3 sensors here. Now the microcontroller, to be able to talk to each of the sensors, it needs a chip select. It needs to enable the sensor, talk to it, and then disable by bringing this line high or low. And the same thing is for the three lines. And then we have the clock that we set to all the same clock to the 3 sensors. The master out, slave in message, and then we have the master in, slave out. Also it's used for a message from the sensors. So let's go through this. So the MOSI, which is the master out, slave in, this is the line where the master sends data to the slave. So you can see here that we send the data. Next we have the MISO, master in, slave out. This is the line where the slave sends data back to the master. Next we have the SCK, serial clock. This is the clock line that synchronizes data transmission between the master and the slave. If the clock is not sending a signal, there will be no transmission. So for this slave to send data back, it needs 2 things. One needs to be chip select, has to be selected, and the other one, you need the clock. It needs to get this signal clock. And finally here we have the chip select, which is slave select. This line is used by the master to select which slave device to communicate with. Okay, let's go to the next subject, with the SPI framework. So we're going to review the data sheet as usual. Next, we're going to develop the framework. We do that by creating our traceability table, and then we put the code together. So let's look at the data sheet. Before we can put together our framework or go through sample programs, first we need to review the data sheet. The data sheet contains all the information on how to program the microcontroller, and you should be familiar with it. So let's head to section SPI. This document is organized by functionality. So that would be section 23, SPI peripherals. And let's jump to the register description. There are 3 registers, and as you know, by manipulating the bits in each of the register, we can control the SPI behavior. So let's look at the SPI control register. In this register, we can enable interrupts. We would enable the SPI. We can decide whether the data transmitted is going to be first the least significant bit, or we're going to send first the most significant bit. Also, in this register is where we select our device to be a master or a slave. We set up the polarity and the clock phase. And finally, we can control the SPI clock rate. Next register is the SPI status register. In this register, we can look at all the flags to see to get information about the events. And also there is one bit that is used for controlling the speed of the clock. Now the final register is the SPI data register. In this register, all the data that arrives or the data that we're going to transmit is going to be placed there. So with this, we have enough information and we can go to our next section, which is going to be putting together our framework. Okay, so let's put together our framework. So the first thing we do is we are going to get information from the data sheet. Here we have the 3 registers, and then in this table we're going to put in here the code required to control these bits on the registers. So it's going to be a number of defines. So this shows you the framework, which is an include file. The name of the include file is framework SPI, so it's right here. Now the source code is generated as before by extracting the contents of the column codes. So we took the stuff on the column code and compile it. To prevent any naming conflict with the existing development environment, the parameter names have been modified by adding an X in front. As usual, I explain this. I put an X in front because this work is done by the environment that you use most of the time. But here we want to know where things are coming from, and also if for some reason you have an environment that doesn't provide these parameters, then you already know how to do the work. Also, as a side effect, we have created traceability of our source code back to the ATMEGA 328 datasheet. So by looking at your source code and going back to these tables, we know where things came from. So let's go through our first sample program. So what we're going to have here, we're going to have an ATMEGA, which we're going to set it up to be a master. It's going to be connected to another ATMEGA, which we're going to configure it to be the slave. And we'll have a LED hooked up to port D0 on the master. And we'll also have a LED hooked up to port D0 on the slave. And in addition to the LED, the master is also going to have a push button. And the idea is going to be that when I press this push button, the LED on the slave comes on. When I push it again, it comes off, on and on. And once the LED gets the push button command, I should say the LED on or off command, then it sends back an acknowledgement. If the master gets the acknowledgement, then flickers this light on and off 8 times, and if it doesn't get the acknowledgement, then it just turns on the LED and leaves it on. So let's go to the statement. When switch is pressed, then transmit a light on command, which is going to be 0x 0f. Flicker an LED 8 times to acknowledge message equal to 06 is received, or keep LED on if no acknowledgement is received. So you flicker the light if you get the acknowledgement, which is equal to 06 8 times, 06 hex, or if you don't get the acknowledgement, then you turn on the LED and just leave it on. If switch is pressed again, transmit the light off message equal to F0. Flicker an LED 8 times if acknowledge equal to 06 is received, or keep LED on if no acknowledgement. So things to remember is 06 is the acknowledgement, F0 is I should start by saying 0F is light on, F0 is light off. So let's go to the slave. If the light on the message equals to 0F is received, then turn on the LED and reply with the acknowledge message, which is 06. If light off message equals to F0 is received, then turn off the LED and reply with a acknowledge message equal to 06. So let's go to the sample program and we'll start with the master. I'll start by giving you a global view of the program. So we have a routine to initialize the port, a routine to initialize the SPI, one routine that is going to care of the transmitting and receiving data. Next, another routine that will take care of blinking the light as needed. Now the main program, what it does is initialize whatever needs to be initialized, and then it takes care of analyzing if the button was pressed and what should be the state of the LED. So let's get into the detail. Now up here I define basically gave names to port B3 and port B4, which are the two transmitting and receiving lines, which is I called it the MOSI, master out, slave in, and MISO, master in, slave out. Next, port B5, I should say, is where the clock output. So I call that port SCK. And finally, the port B2, which is where the chip select output comes out, I called it SS. So let's look at the init ports. This is the routine that's going to initialize our ports hooked up to the LED and to the switch. So the LED is hooked up to port D0. So I set port B0 to output. The switch is hooked up to port B1. So I set up port B1 to input. I also set in port B1 I enable, I should say, a pull-up resistor. Next, we have the init SPI as a master. So first thing I do is I set up the MOSI, SEK, and chip select ports to output. Next, I set up the SPI to be a master, and also the output clock to be the system clock divided by 16. And that's what this line is doing. Next, we have the SPI transceiver, receiver, and transmitter. So the first thing I do is I set up the chip select, bringing the chip select from high to low. That selects the slave. Next, I store the data that I want to transmit in the DR0 register, data register. Next, we go around and around in the while loop until the transmission is completed. What this is doing is basically comparing the flag which states that the transmission has been completed. Next, we release the slave by bringing the port B2 to high. And finally, we take the data that we received and return it. Every time we send data, we also receive data. Next, we have the LED blink. So the first question this routine asks is the data that we receive after sending the command, was it the acknowledgement? If the answer is yes, then we turn on and off the LED hooked up to T0 8 times. Now, if the data that we receive is not the acknowledgement, then we turn on the LED and just leave it on. So let's go now to the main program. So we initialize the port, initialize the SPI, and then first thing we do is we wait 80 microseconds. So the reason why we're waiting here is to account for the debouncing of the switch. Now, every time we push the switch, there is a whole bunch of bouncing. And by testing, experimentation, I figured out the correct number, I should say, was 80 microseconds. So the first thing this program does is checks the current state of port B1. That's where the switch is hooked up. Next, we have an if statement which compares the current state of the switch, which we just read, with the prior state of the switch. Now, if the prior state was high and the current state is low, that means that the switch was pressed. In which case, we ask, was the state of the LED on or off? If the state was off, then we need to turn it on. So the first thing we do is we say SPI transceiver, and we send the turn on LED command. Next, we change the state to LED now is on, and then this data is going to contain the data that was sent by the slaves. So we go with this data and call the LED blink routine. Like I noted before, the LED is going to check if the data was the acknowledgement, in which case it turns on and on the LED 8 times, or if not, it's just going to turn on the LED and leave it on. Next, we go to the loop, but this time we check again if the switch new state, current state, and all state goes from high to low, and if that's true, and the LED state is not off, then what we need to do is turn off the LED. So the data, we send the command to turn off the LED. Next, we change the state to say that the LED was off, and then we check for acknowledgement. Now, the last thing I always do before leaving this, before going around on the while, I should say, last thing I do, I say the button old state is equal to the button new state. So let me recap. We check the state of the button. If the light is off, we turn it on. If the light is on, we turn it off. If the taste doesn't go, I should say, from high to low, then we know the button wasn't pushed and we do nothing, and we just equate the old state to the new state. So I think that gives you a good idea what this program is doing, or at least a running. Okay, so next we're going to look at the program from the slave standpoint of view. So this is the schematic of the slave. So let's get going with the slave. I'll start by giving you a global view of the program. So we have an init ports. That's a routine that's going to initialize the ports. Next, we have a routine that's going to initialize the SPI as a slave, followed by a routine which is going to be responsible for sending and receiving data. Next, we have the main. In the main, we're going to initialize whatever it needs to initialize, and we're going to take care of turning on and off the LEDs as requested by the master. So let's get going on the details. So first I took pin B4 and pin B3 and associate them with the name MOSI and MISO. And that's just for my convenience, so it's easier to program. Next, pin B5 was associated with the name SEK. That's the output for the clock signal. And then I took pin B2 and associated to the chip select. So let's start with the init ports routine. Here what we do, we set pin B0 to output. That's because we're going to use this pin to turn on or off our LED as commanded by the master. Next, in the SPI init slave, what we do here is we set our MISO, master in, slave out, port to output, and then we enable our SPI. Now the SPI transceiver. First step, if we place the data into the data register. And then we go around and around and around until the flag that states the transmission is completo becomes true. And then we jump to the next step, which is that we already have the data and we return the data. And that's what this return is doing. Next we go to the main. The main program, first thing it does is initialize the SPI. Next, initialize the port. Now what is the while loop doing? So it's going around and around and around and doing the following. First, it's going to try to transmit the acknowledgement. But this acknowledgement is not going to be transmitted until the slave gets the data from the master. For the master, is when it sends the data, it's going to give it the clock it needs to send the acknowledgement. Now what do we do with the data? First, we ask if the data is the on command, in which case we turn the LED on. Now if the data is not the on command, then we ask, is the data the off command? If that's true, then we turn off the LED hooked up to port D0. The final thing is I delayed the loop by 20 milliseconds. That's just a number that I put in by experimentation and made things go smooth. But there's nothing magical about that number. So with that I think I've given you a good idea how the slave works, and we can continue to our next subject. Okay, so let's continue. So we got to the summary. So today I gave you some background on the SPI. We talked about the registers and how to configure them. Next, we put together the framework. And finally, we went through a sample program. Well, I hope that concludes the presentation, and I hope you've enjoyed it. Thank you very much.